Hello everyone, my name is Dr. Mirikos. I am an assistant professor in the Department of Chemistry, SRM Institute of Science and Technology. So today we will discuss the coordination chemistry. We will learn about ligands, coordination number, geometry of complex, isomerism, bonding theories, crystal flip splitting, magnetic properties, and color of compounds, and many more. So let's begin. In the oneness theory, first we supposed to know what is the oneness theory. Scientist Warner first proposed that a metal ion shows two types of valency. Primary valency is the oxidation state, and secondary valency, while secondary valency is the coordination number. Coordination number tell us how many donor atom or ligands are directly attached to the metal ions. Now the ligands. Ligands are the molecules or ions that donate a lone pair of electrons to the metal center. They are usually anions or polar molecules. The ligand metal bond formed is called the coordinate bond. So we can see here a picture here where we can see a central metal atom and ligands are attached with the central metal atom, where the central metal atom is cobalt and all the ligands are here. The this one, all these are ligands here. Okay. Now let's move to the coordination numbers. What is the coordination numbers? So coordination number and geometry. Coordination number determines the the possible geometry of a complex. Common coordination numbers are 2, 4, 6, but coordinate numbers from 2 to 9, even up to 12 is also possible. We can show you here. Yeah, first this is the linear one, 2 with coordinate number 2, then 3, all having some specific structure. Let's say for the coordinate number 2, it's showing the linear structure, and the coordinate number 3 is trigonal planar. So we'll move to some more higher coordination numbers. Let's say the coordinate number 4. There's two different kinds of possible. A coordinate number 4, tetrahedral and square planar. Okay, so this is a square planar and this is the tetrahedral. So four coordinate number, two different kinds of geometry is possible. Now let's move to the coordinate number 5, square pyramidal and trigonal pyramidal. Two different structures are possible here. Now, let's move to the transformation of octahedral geometry. Okay, so coordinate number 6 is the most common in the coordinate chemistry. The usual geometry is the octahedral, as seen in the hexaamine cobalt ion. Okay, so let's see this one. Now, after that, many more different possibilities are there. Coordinate number 7, 8, and more. So what we can see here, trigonal prismatic geometry. It can be related to the octahedral geometry. If a triangular face of an octahedral rotates relative to the opposite face, it passes through a trigonal prismatic arrangement. Coordination number 8, 7, 8. Different kinds are possible. So let's suppose the 8. This 8 quadrant complex often shows square antiprismatic dodecahedral geometry. Both can be viewed as distorted cubic arrangements. Now, also 9, we can see the tricap trigonal prismatic structure ML9 and also 12 icosahedron. Now about the chelating ligands. What is the chelating ligands? So now we know the ligands, but what is the chelating ligand? A chelating ligand attached to the same metal through two or more donor atoms. The word dentate means that the teeth. So you can see here, denticity means the how many teeth it have. But when it connects to two metals, so then we call it like a as a chelate ligands. Okay. So a bidental ligand may either be chelate one metal center or bridge between two metal centers. So let's say the pyrazine is a bidentate, but when it connects two metal ion, it acts as a bridging ligand rather than a chelating ligand. So we are showing here some example of the bidental ligands, polydental ligands. So we see here, let's say bidental ligand, ethylene diamine. These are the donor center, the lone pair of electrons, bipyridine, okay, orthophenethylamine, oxazole, carbonate ion, and these are the polydental ligands. And this is very well-known one polydental ligand. This is called the EDTA. So here total six coordinates is possible. So one, two, three, four, five, six, 8, 9, 10, 11. Okay. So total these are the possibilities, but mostly it binds with the six ways. So total six ways it can bind. So this is called the EDTA, ethylene diamine tetraacetate. Okay. So these are all about the uh, ligands, polymetal ligands. So metal EDTA. So we are showing here how it makes the bonds. Let's say one central metal ion is here. So how the EDTA is making the bond we are showing here. So finally made a chelate complex. Why it make the chelate complex? Because after making the chelation, the complex become extremely stable. So that's why it makes the chelate complex. Now the classifications of the coordination compounds. So um, first we can see here types of isomerism. Structural isomerism includes the ionization, hydrate coordination, and linkage isomerism, whereas stereoisomerism includes geometrical and optical isomerism. Okay. Now, each of these hydrate, ionization, coordination, and linkage, geometric and optical, each of them we will try to understand with proper examples. Let's see. First, ionization isomerism. So, what is the ionization isomerism? So, ionization isomerism is a ligand inside the coordination sphere where it exchange with a counter ion outside the coordination sphere. Therefore, the ions produced in solution are different. So, let's say for here Br minus and here SO4 minus. So, anion will be different. Okay. So, let's say for the hydride isomerism. Hydride isomerism, water molecules may be inside the coordination sphere or outside as water of crystallization. Chromium chloride hydride gives violet green isomers depending on the number of coordinated chloride and water molecules. Mhm. Now, what the coordination isomerism? Coordination isomerism occurs when both cation and anion are complex ions. Ligands exchange between the two metal centers with the total composition remain same. So you can see here total composition for both cases remain same. They just change the coordination sphere. Now about the linkage isomerism. Linkage isomerism occurs when an ambident ligand coordinates through different donor atoms. The composition remains the same, but the point of attachment changes. This is called the linkage isomerism. Okay, we can see the color also is different for both cases. Except for the ONO, the linkage is with the nitrogen, and for another one, it's linkage with the oxygen. Except for the thiocyanate and isothiocyanate. So in one case, it is the first case, it is attached with the sulfur. In the next case, it is attached with the nitrogen or the isothiocyanate, and their characteristic color is also different. Okay, I guess you got the clear idea. And let's say for the nitrite, and thiocyanate, all having the ambient ligand as we have discussed before. Okay, now let's begin with the stereoisomerism. Okay. Geometrical isomerism. Geometrical isomerism is most important in square planar and octahedral complex. The ligands are bonded to the same metal but occupy different position in space. Let's say for the square planar Ma3b. A3b means like all having same ligands. A3, 3A complex. That means all having same. Only B is different. So for square planar, they may either be complex, all four positions are equivalent, therefore only one geometrical isomer is possible here. So we can showing in this picture. Okay. Let's say for the Ma2B2 type or square planar Ma2B2 complex, two isomers are possible in cis form. Similar ligands are adjacent in trans form. Similar ligands are in the opposite form. Okay. These are the cis square planar upon Ma2B2 form. Okay. Now about the cisplatin and transplatin. Cisplatin and transplatin have the same formula, but their spatial arrangements are different. Cisplatin is medically important and used in cancer treatment, whereas transplatin does not show any kinds of comparable therapeutics activity. Okay. Now about the octahedral MA5B or MA4B2 complexes. For octahedral A5B complex, only one arrangement is possible. For the A4B2 complex, cis and trans, both are possible. Okay, cis and trans octahedral complex. So, um, let's say for in the cis form, the two fluoride ligands are adjacent to each other. Okay, here you can see the two fluorides are in the adjacent to each other. In trans form, they are in the opposite direction of each other. Both have the same composition but different spatial arrangement. And their color also you can see is violet in color and this is green in color. So we can really understand how much important is the position of the ligands in the coordination chemistry. Now the facial and meridional. In facial isomerism, three similar ligands occupy one triangular face of the octahedron. In meridional isomerism, the three similar ligands lie along a meridional plane. Okay, these are the basic difference. So in this one, we can see the facial. That means it can make a face here, and for meridional, they are along the axis. Okay, this is the facial or meridional. We call it like short form, fake mark. Okay, so this we can differentiate them. I guess it's clear for you right now. Let's now go to the next one, the stereoisomerism. So, the stereoisomerism, um, we're supposed to know first the chirality in complexes. So, We supposed to know the enantiomers, what is the resin mixture, all of this. Okay. So let's first do the optical isolation. Optical isolation occurs when two structures are a mirror image but cannot be superimposed. These kinds of molecules are called the chiral, and the two forms are called the enantiomers. So let's say for if we take our hands, they are non-superimposable. They are mirror image of each other. So they are a kind of example of enantiomers. Now we shall pursue what is the plane polarized light. Why we need this plane polarized light? Because in the plane polarized light, enantiomer has some specific characteristics. It can change or rotate the plane polarized light. So what is the plane polarized? Optically active compounds rotate the plane of plane polarized light. One enantiomer rotate the light in one direction, and another form in the other rotates to the same amount to the opposite direction. These are called the enantiomers. Now, plane polarized light means a light if we chop it in one direction, and only unidirectional light if we pass through a filter. Yeah, this light is now it's like only unidirectional. So as we are showing in this picture, unidirectional they have some like vibrations, but they are unidirectional. Unidirectional only one direction like this one. Okay, we can see here like different directions. Okay. But here only you can see only one direction. So when these lines can be polarized by using some material, we call it like a plane polarized light. And this one, only the enantiomers can rotate these lights. Mhm. I hope it is clear for you. So this is the end of the slides of this first chapter of the coordination chemistry. So in the next chapter, we'll discuss more on this enantiomers, diastereomers, and many more. Okay, thank you. See you in the next video.